Hi everyone! I hope you all had a good break. Today we're going to be learning about waves. If you have a question at any point in time as we're going through, don't hesitate to ask. You can either ask over your microphone or you can record it in chat. Now, one thing to be aware of is my webcam is over here, but my laptop's actually over here. So if you ask it in chat, it may take me a moment to see it. And if you see me glancing over this way, it's because that's where my laptop is, so that way I can see if you are asking any questions in chat. So we're going to kind of expand on some of the topics that were covered in those videos that Mr. Dudish sent us. And we're also going to kind of refresh some of the concepts that we talked about at the end of last semester about simple harmonic motion. Now, in the videos, we learned about transverse and longitudinal waves. And I want to start by showing you a short video that I recorded on showing you what these actually look like, because I think sometimes it's helpful to, instead of just having the abstract concept, to also have kind of a visual of what these things look like in real life. Hey everyone! This week we're learning about waves. I want to take a moment to demonstrate for you what transverse and longitudinal waves look like. So first we'll see an example of a transverse wave. So I have here this honor chord, and if you want to follow along at home, graduating seniors, just take an honor chord, plunk something down on top of it, and then give it a little flick. And you'll see that it goes a little bit fast, but you'll see that that shape kind of travels down the line. So we just give it a little flick, and you get a little bit of a wave shape that goes, it starts out up here and it goes down there. Now, if instead of flicking it just once, what if we moved it back a few times? You can see we start to get a wave shape with multiple fronts. So next we're going to do an example of a longitudinal wave, and I'm going to use a slinky for this. So if you're following along at home and you happen to have a slinky in your old toy box or something, feel free to dig it out and try this as well. So what we're going to do is we're going to take our slinky and we're going to stretch it out a little bit, and we're going to send a wave through it by just jostling it, and you'll notice that the wave front starts in one place and it kind of travels down. So you bring it up, so there are places where it's stretched out and places where it's compressed. You can kind of see that compression front moving through the slinky. Now, when we're thinking about waves, we can think about kind of two different types. There are at least a couple of different ways of thinking about them. So there's what I'm going to call the snapshot view. And if you think about when, the transverse wave, when we were looking at it, it had those wiggles, and they're at distinct places in space. So you can graph a wave in XY space. So I'm going to draw in a coordinate axis. And both these are going to be distances. I'm just going to use y and x to denote them. So I'm going to call this y, and it's going to be in meters. This one is x in meters. And our wave might look something like this. Now, there are some key features of a wave that we might be interested in talking about. The first one is going to be the amplitude. And that's going to be the distance from our equilibrium point to our furthest displacement. So going from our 0 point up to our peak or down to our trough. So I'm going to use this as an example of our amplitude A, but this distance is the same here, here, and here. You could mark any of those as A as well. So an A stands for amplitude. Now we also have, can identify our peaks and our troughs. So this right here is going to be, actually, yeah, we'll do this one. This is our wave peak. And this down here is a trough. So the peak is, your highest point, the trough is your lowest. Now when we have a graphed in XY space, the distance between peaks or between troughs is called the wavelength. So this distance here That's our wavelength, and we use the Greek letter lambda to denote it. So lambda is our wavelength. So are there any questions so far? All right, so we can also think about waves. If we pick a specific point on our wave and follow it through time, we can think about them in that way too. And that, you're going to later on hear the term history graph to use for tracking a specific point over time. And so we can also think about in that frame of reference. So I'm going to erase this, and the graph is going to look very much the same, but the difference is going to be what's on the x-axis. So let's suppose that we want to track the end of our rope. So when we take our rope, we give that end a little flick to get the wave going, and we're just going to track the very end point over time. And what does it do? Well, we're going to get a graph that looks something like this. So we start by pulling that endpoint away from its kind of point of origin, and then it kind of settles back down. And it's going to kind of oscillate as the rope oscillates. And so we're still going to have an amplitude, A, so that's very much the same type of thing. We're going to have peaks and troughs. So this is a peak. And I should mention what's on our axes. So this one is going to be our displacement in meters. And we're going to be talking about the vertical displacement only. So even though I'm using an x, where it's the vertical displacement because the point is at its fixed position in xy space, or in the along the horizontal axis, but it's moving up and down. So we're just tracking the up and down motion of it. And then this axis is going to be time in seconds. So we have our peak, we have our trough. But now, instead of the distance from peak to peak or trough to trough being wavelength, since our axis is time, this is going to be our period. So when you plot position versus time, that distance is the period. And the period is just how long does it take for the wave to complete one cycle. So are there any questions so far? All right, so the next thing we're going to do is I'm going to introduce a couple of the equations. So one of these, at least, we've seen before when we were talking about simple harmonic motion. So last winter, December-ish, when we were talking about simple harmonic motion, we introduced the idea of frequency. And the frequency of a wave, we're still going to define the exact same way that we did last time. So our frequency is equal to 1 over the period. So F is frequency. Now, since it's 1 over the period, well, periods are measured in time, units of time, so seconds. So the units of frequency, I'm going to use this bracket notation to mean units. So the units of frequency are going to be inverse seconds. So it would be seconds to the minus 1. And that's the same thing as a hertz. So we could say that it's seconds to the minus 1 or hertz. Those are both equivalent. So either of those units is fine depending on which one you want to use at a different time. Now, we also learned a new equation relating to the velocity. So if you want to know how fast a wave is traveling, it's related to the frequency and the wavelength. So the velocity of a wave is our wavelength times our frequency. So v is velocity. So if you know the wavelength and the frequency of a wave, you can figure out how fast it's traveling. And if you have light waves or sound waves, the velocity is actually a constant number, so if you knew one of these other two, then you'd be able to solve for the other one. So are there any questions on this so far? All right, so the next thing we're going to do is we're going to derive the equations for position as a function of time, velocity and acceleration. If you had me last semester, you've already seen this derivation, but I imagine we're probably all a little bit rusty since we haven't touched simple harmonic motion since last December. So we're just going to do a quick derivation to see where those position, velocity, and acceleration equations that the book gives us actually come from. So, and Mr. Douche has posted a sheet that has these equations on them, and I'm kind of showing you how do we get these equations. And so to work through our example, let's suppose we have a spring and it has a fixed end. So our spring is attached to the wall, and at rest it looks something like this. Now let's suppose we pull on the end of the string and kind of stretch it out a bit. So this is this equilibrium position right here. And now we pull on that one end, and so it's stretched out. When we take this end and we let it go. And so we're going to start out, we're going to be displaced a good distance from equilibrium. When we let it go, it's going to start moving this way. So if we pick up a specific point, so I'm going to pick this point right here. We're tracking this point over time. So we want to know what does this particular point do as over time. So we're going to it's going to start out farther away from equilibrium. It's going to come in, hit the equilibrium position, overshoot, and then it's going to come back and it's going to oscillate back and forth. If it's true simple harmonic motion, it would just oscillate back and forth indefinitely with that same amplitude on either side. So if you want to see what this would look like, the motion of that, we're going to put position in meters on this axis, and we're going to put time in seconds on this axis. And so what we're going to do is it starts out, if we make this the positive direction, it's going to start out at some height up here, and then it's going to come down, hit its equilibrium position, overshoot, come back, and it's just going to oscillate back and forth. So it's going to look like a cosine graph. And the equation that the book gives you is that our position as a function of time is equal to our amplitude, so just how high is it going each time, cosine 2 pi times the frequency times the time. So that would be our position equation. Are there any questions on how we derived this? All right, so if you want to think about how to get to velocity from position, we know that velocity is the slope of our position graph. So we're going to look at our slopes at different points along our curve and use that to figure out what shape would our velocity graph have to have. So I'm going to start at this top point here, and we can see it's flat here, so this has no slope. And then we have a little bit of a negative slope, steeper negative, really steep negative, and then it's going to kind of flatten out a bit, but still negative. And so if we were to draw what that would be, well, we're starting out, we have no slope, so that would be 0. And then we have a little bit negative, more negative, really negative, so right here is where we're most negative, and then we're going to kind of come back up because we're less negative, but still negative, and then here we're going to have no slope, and then we're going to kind of continue. And you can see this looks kind of like a sine graph, but an upside down one. So the velocity shape should be an upside down graph, and indeed we find out that it is. So to sketch velocity versus time, our velocity is in units of meters per second. Time is in seconds. And we're just going to have an upside down sine graph. And when we go to the equation, so it's going to be a velocity as a function of time. Now there's a coefficient out front. And the way you get this coefficient is from calculus. So if you're taking calculus, then you know that velocity is the derivative of position. So if you're wondering where this funny coefficient out front comes from, it comes from taking the derivative. But for the purposes of this class, we don't need to worry about where it comes from. That's just if you wanted to know why is there this funny coefficient out front now, it just comes from velocity being the derivative. So we're going to have a negative sign because it's upside down. And then we're going to have 2 pi times the frequency, which is our funny coefficient from calculus. We're still going to have an amplitude A. And then we're going to have sine of 2 pi times the frequency. So are there any questions on how we derived our velocity equation? Alright, so the last quantity we might want to know about is the acceleration. And we know that acceleration is the slope of our velocity graph gives us acceleration. So if we look at our slope at different points along our curve, we can see we have a negative slope here, and it gets less negative. It becomes 0, and then it starts going positive. So if we were to graph this, it's going to look something like, starts out negative, comes up to 0, it's positive, and it's going to kind of, you can see that it's starting to look like a cosine graph, but upside down one. So our acceleration is going to be an upside down cosine shape. So our acceleration is a function of time graph, so this is acceleration, units of meters per second squared, time in seconds. And again, the coefficient out front is going to come from calculus, so acceleration, turns out, is the derivative of velocity. So you're going to get a funny coefficient out front, but the negative cosine piece, I think, is conceptually easy to see where that one comes from. So our final equation is going to be that our acceleration as a function of time is equal to 2 pi times the frequency, this quantity squared, times our amplitude, sine 2 pi f, and we just said it's upside down, so we also need a negative sign out front. So negative of all this stuff. So are there any questions on this? So for those of you who had me last semester, you may be wondering what happened to Cupcake and Molly. And lucky for you, they're returning in an example today. So for your amusement purposes, I'm going to draw Cupcake the kitten and Molly the puppy on the board, and we're going to do a little exercise involving them. So, an artist I am not, but we have our friend Cupcake the kitten, and Cupcake is crying for her dinner. And we have Molly the puppy over here. And Molly sees a bird and she starts barking at this bird. And so we're given that the frequency of Cupcake's cry, which we're going to use a little sub c, so f sub c for Cupcake, is 3.5 kilohertz. And the frequency of Molly's bark is 1.5 kilohertz. And so we want to know what is the wavelength, excuse me, what is the wavelength of each of these sounds given that the speed of sound is about 343 meters per second. So v sub s is 343 meters per second. So any sound, whether it's Cupcake's cry or Molly's bark or any other sound, is going to travel at about 343 meters per second. So if we want to solve this question, we're going to have to pull out our equation for velocity was a function of wavelength and frequency and rearrange it a little bit. So we know that v equals lambda f. So if we're looking for lambda, we're just going to divide both sides by f. We'll have that lambda is equal to v over f. And we just said that v was 343 meters per second. And then the frequency of Cupcake's cry, we said, was 3.5 kilohertz. So we have to convert that into hertz. So that's going to be 3,500 hertz. Now remember that hertz is inverse second. So the inverse seconds here and here are going to cancel, and they're going to give us units of meters like we need. So we're going to find that our wavelength, and I'll give this a little sub c, so lambda sub c is equal to, about 0.098 meters. So if you were to measure the distance between peaks of the sound waves of Cupcake's cry, they would have an actual distance of about 0.098 meters. It's a little weird to think about that sound has this measurable property of it, but sound and light both act as waves, so we can actually measure the distance between the peaks. Now for Molly, it's going to be the exact same thing. So we're just going to use this formula over here, but we're going to plug in a different frequency. So lambda sub m is going to be 343 meters per second divided by 3,500 hertz. And when we plug that in, we get about 0.2287 meters, which to two sig figs would be about 0.23 meters. So are there any questions on the first part of this problem? Alright, so the next thing we want to know is, if Cupcake and Molly are each standing 10 meters away from you, how long will it take for their respective sounds to reach your ears? So to set up the situation, I'll use me as the example person. So we have Cupcake over here, we have me over here, and we have Molly over here. And we know this distance here is 10 meters, and this distance here is 10 meters. We want to know how long will it take for each of these sounds to reach my ears. Now, the thing about sound is that all sounds travel at the same speed. So if we solve this problem, since our speed and our distance are the same, if we solve this for one of these situations, we solved it for both. So remember that velocity is displacement over time. So v equals delta x over delta t. We want to know the time, so I'm going to multiply both sides by delta t and divide by v, and we're going to get that delta t is equal to delta x over v. And our displacement for either of these is 10 meters. And then the speed of sound is about 343 meters per second. So if we plug this into our calculator, we get about 0.02915 seconds, or to 2 sig figs, about 0.029 seconds. So it's going to take a small fraction of a second for that sound to reach your ears from either of the animals. If there are no further questions, then that's all I have planned for you for today. Don't hesitate to contact me via email if you have anything you want to see covered, or if you have questions on the homework or anything like that. And have a great day.